Everyone, and welcome to Physics Lab number 2. In our last lab, we observed the interactions between two charged objects. We could see that something was happening, but we didn't have the tools to measure or predict those interactions in detail. So that's exactly what we'll focus on today. Going beyond just observing and actually predicting, testing, recording, and explaining what happens when objects become charged. In this lab, we'll be working with different materials and using an electrometer to determine the sign of charge after rubbing rods with different cloths. This will help us build a reference guide that we can use throughout the experiment. Once we know how to reliably create positive and negative charges, we'll be ready to test how those charges interact with neutral, conductive, grounded, and isolated objects. For example, we'll explore how a charged rod interacts with a dangling piece of aluminum foil, first without touching it and then after making contact. We'll then move on to a pith ball, which is another small conductive object, and compare how its behavior changes before and after touching the rod. Each step will challenge us to make predictions, observe what really happens, and think about why our results may or may not have matched what we expected. Finally, we'll introduce the concept of polarization and induction, important processes that explain how objects can become charged simply by being near a charged body without direct contact. By the end of the lab, we should have a deeper understanding of how charges move, how they transfer, and how they can even be induced in neutral materials.
Using the materials listed, we are conducting an experiment to demonstrate the transfer of electric charges and the resulting attractive forces. We used a pith ball, cotton cloth, fur cloth, silk cloth, PVC rod, acrylic rod, glass rod, aluminum foil, and electrometer. For our hypothesis, we concluded that if an acrylic, PVC, or glass rod is rubbed with wool, fur, and silk separately, then the rod will show different levels of electric charge, because each material has a different ability to donate or accept electrons. Thus, if an electrically charged rod is brought near small pieces of aluminum foil, then the foil will be attracted more strongly to the rod with a greater electric charge due to stronger induced polarization forces.
For this procedure, we used two separate rods for every part, but specifically for part A, we focused on observing the reactions, if any, for a charged rod on a piece of aluminum foil. So first we used the uncharged rod, in which we saw little to no attraction, but when charging with fur and silk, we saw a notable pull towards the rod without coming into direct contact with the rod itself. And then for part B, we did a similar protocol, first using the uncharged rod and then charging it, but this time we allowed it to come into contact with each other. And similar to our first interaction, there was an obvious attraction between the charged rod to the aluminum. And for part C and D, instead of using a piece of aluminum foil, we used a pith ball to test the attraction, repelling of the charged rods. And in part C of our experiment, we made predictions that the rod would attract the pith ball if it was charged rather than uncharged, which was proven to be correct. And for part D, we did the same steps, except we allowed them to touch each other, where we witnessed a very strong pull. And for part E, we used charged rods in order to make a scenario for induction via a sphere and make an educated guess on whether the sphere would make or would have a negative charge.
Here's our complete data table, which summarizes the results from parts A through D of the lab. The rows show the different parts of the experiment, and the columns show which rod and cloth combination we used. Each box describes whether the interaction was attraction, repulsion, or if no noticeable effect occurred. Starting with part A, when we brought the rods near the grounded aluminum foil without touching, we found that acrylic rods with fur or silk caused attraction, while PVC rods and any wool trials showed no interaction. This shows that acrylic was better at inducing a response in this setup. And in part B, after touching the foil with the rods, we saw more consistent results. Both acrylic with fur and silk caused attraction, and PVC with fur also attracted. However, PVC with silk and wool still had no effect. This supports the idea that conduction or direct contact produces stronger charge transfer than induction alone. Moving to part C, which used the isolated pith ball, only PVC with fur induced a repulsion. All the other materials, including acrylic, showed no effect, and this indicates that the isolated pith ball was harder to influence without direct contact. And finally, in part D, when the rods touched the pith ball, nearly all combinations except wool caused attraction. So both acrylic and PVC rods with fur and silk produced attraction, and this confirms that conduction is the most reliable way to transfer charges in our test. So overall, this table highlights how the method of charging and the type of material used affects the outcome. So now that we've looked at the raw data in the table, this slide is more about what the results actually mean. So the first thing that stood out was induction, and that's when you bring a charged object close, but you don't touch it. And in our test, like parts A and C, it sometimes worked and we saw attraction or even a little repulsion, but most of the time we got nothing. And that kind of makes sense. Induction is only temporary. The charges in the neutral object shift around a little, but if it's not strong enough, you don't really notice anything, and that explains why those results felt inconsistent. Then, when we switched to conduction in parts B and D, everything changed. As soon as the rod actually touched the foil or the pith ball, we saw attraction in almost every case. That's because with conduction, electrons are literally being transferred, so the objects end up carrying charge. It's way more reliable than induction, and the data backs that up. And something else we noticed was the difference between materials. So acrylic rods worked really well with fur and silk, and they almost always showed attraction. PVC, on the other hand, was kind of hit or miss, and wool barely did anything at all. And no matter which rod we use, that matches what you'd expect if you look at the triboelectric series, and some materials just don't build up charge as easily. So if I step back and look at the big picture, induction gives us weak or temporary results. Conduction gave us strong and repeatable results, and the type of material made a huge difference. Acrylic was the best, PVC was average, and wool basically failed. So overall, the data lined up with what we've learned about electrostatics. Conduction is the most effective way to transfer charge, while induction is less reliable, and the material matters just as much as the method.
Considering the observations, the lab provided insight on the function of charge and how it influences the type of charge that an object can acquire. To assess this, we understood the phenomenon of charge and what particle is responsible for this transfer of charge from one object to another through the movement of electrons. As the only particle that lies in the valence shell of atoms, they are easily removed through agitation, hence the rubbing of materials which breaks those intermolecular bonds. For this reason, we utilized various materials of cloths and rods to demonstrate the force exerted. Importantly, the procedure originally called for an extra rod made of glass. However, the ends were shattered, which presented a hazard to work with and therefore not utilized in this experiment. Overall, our qualitative analysis indicates the material acrylic with fur and silk, which presented charge transfer and attractive forces when we more consistently compared to examining PVC, the other rod material, which displayed varied results of attractive, repulsion, and no forces. Lastly, wool was the only cloth material that did not seem to show any capability of charging the rods. However, it can be inferred that the inclusion of glass may have resulted in displaying a charge which could have resulted in either charging the glass rod positively or negatively. To conclude, the lab was able to extract observable data and investigate the force that is displayed through charged objects. It is suggested that the charge acquired is material dependent and therefore not uniformly transferred on all objects. We would like to thank you for your curiosity and attention to learning the forces that are at play when an object acquires charge. If you have further questions, please let us know in the following email. Stay curious and dare to know.